The figure below shows an idealized diagram of a 118-meter long and 70-meter wide section of a river. It's 118 meters this way, 70 meters that way. It's a section of river. And the cost of laying cable on land along the river's edge is $10.16 per meter. So like this right here, this would be along the river's edge. The cost to lay cable underwater is more. That costs more. They got to have scuba divers go down and, underwater welding is very expensive, all that kind of stuff to put this cable right here under the water to cross the river. A company is contracted to install cable from point A to point C on the other side of the river. In order to minimize cost, they must determine the optimum point at which to leave the far side of the river and bring the cable across to point C. In order to determine this, they will need a function that gives the total cost of laying cable from point A to some point B, right, A to B, along the same side of the river, then across the river to point C. Let x equal the distance the cable will travel on land along the far side of the river before it is brought straight across to point C in meters, i.e., let x represent the distance from point A to the hypothetical point B in the figure. Yeah. So we'll say, okay. So from here to there. Oops. That is x. That's what they're saying. So in other words, we're trying to find the point B. Like, where should they go? How far should they go before they go across the river? It's cheaper to lay cable over here when you're not doing underwater. It's only 10.16 a meter. Whereas it's much more when you start going across the river. But I mean, you might think, well, okay, well then just go all the way and then just go straight across the shores. Well, problem is that's a lot more cable. That's probably not going to be the cheapest way to do it. And you think, well, just go straight diagonal, and that's all water. That's probably not the cheapest way to do it. There's some point in between. B, where is it exactly? Where you're going to have, some land and then some water. It's not too long and yet you don't have too much water, which is more expensive. What is that optimum point? This is what engineers calculate as things like this. What's the best way to lay the cable? So, how are we going to do it? So they say, first off, determine the formula for the total cost of laying the cable from A to B to C in terms of X. From A to B to C. What's the total cost of all that cable? Okay. Well, we know this is X. Let's get this length first, and then we'll get the cost. How far is it from B to C? What we can do is we can say, well, we have a right triangle right here, right? And we know how big this piece is. Do we? Yeah, it's 118 minus x. Do you see that? Why? Because all the way across is 118. Take away x, this is the leftover. It's the difference, right? All the way across is 118. Take away the first part x, you're left with this. So 118 take away x. So there's that. Now this is 70, so the other side is clearly 70. We have a right triangle. We can do the a squared plus b squared is c squared. Tracking with me? A squared plus b squared is c squared. This is our c. Little bitty right triangle right there. So we go, okay. Right, whenever you have a right triangle, you can do that. So 118 minus x squared, that's a, plus 70 squared, that's b, equals c squared. How do we get just c? You know. Take the take square root on. Let me try that. Square root this side. Square root that side. Square root both sides. And so then we have square root of 118 minus x squared plus 7 squared. By the way, you might think you can just cancel these squares. You can't because of the plus sign. If that was times, we could totally do that. But remember, pluses and minuses, nothing nice ever works in algebra rules. We can't cancel the squares. It has to stay just like that. You can prove it with numbers, but we don't got time for that. So there's C. So let me write this in. So this distance right here then is this. Oh, I thought I had my tool wrong. Is the square root of 118 minus x squared plus 70 squared. That's how long that is. Now, how do we get cost? Well, so we have this piece of cable and that piece of cable. We just multiply each of those by the charge, right? So this is X meters at 1016 a meter. This costs $10.16 per meter delay. So it's 1016 times X. And this stuff right here costs, what is it? 1558. 1558 delay. So it's 1558 times that other piece of cable. That'll give us the total cost function. Does that make sense? We just found each piece multiplied by the cost per meter, right? This is how many meters. This is how many meters times the cost per meter. Add them up. That's the total cost of laying cable. So that's all we're going to do on this one. That's just the setup. This is just a setup problem. So then to finish it up, we would then say, okay, now find the point, find X, like how far should X be to minimize the total cost. So you would take this function, take the derivative, and set it equal to zero and solve for X. Find the value of X that makes this total cost as low as possible. That'll find the spot, wherever it is, that you should run the cable to and then across the river to keep this as cheap as possible. That's how engineers do that. But we're just doing setup on this one. So we're done right there.